Hello, and welcome to Protein Synthesis Mutations/Review. So over the last couple of days, you've been working on some protein synthesis style questions. You went over the notes, and at the very end were some mutations. So here is a review of that with more practice, because you will have one assignment that will deal with these mutations. So definitely pay attention to what's going on, and with your chart, you should do all right. And I got my chart handy. All right. So what we have here is the DNA, which is your genetic material, which we learned about. And the genetic material is found in the nucleus, which you guys know. So the DNA lives in the nucleus. And it does not leave the nucleus. But we need some information from the DNA to get out into the cytoplasm to find these ribosomes to code for proteins and traits and things. So you need to get this information out. You're going to get it out with the help of a molecule called mRNA. So what happens is the DNA codes for mRNA in the nucleus in a process known as transcription. And you cannot do that unless you have the help of an enzyme. And the enzyme is known as RNA polymerase II. And what that is going to do is it's going to take the DNA and it's going to make mRNA. But there's some rules. mRNA has a U instead of a T. The A, the G, and the C are the same. So if that's your DNA, and let's say it's ATGC, the mRNA from that is going to be UACG. So remember, it's complementary, but there are no T's. So we'll see some more of that coming up in a second. Okay, so let's take a look here a little bit closer now. So after the mRNA is produced, it's going to leave the nucleus and head out to the ribosome. The ribosome is in the cytoplasm. Once there, these cool molecules called tRNA are going to bring very specific amino acids and begin building this thing called a polypeptide. Now we saw all that in the last couple of videos. This is just now practice questions. But this process is known now as translation. So let's see what we got. We got DNA. Once again, you know it's DNA because it's double-stranded, and there is the letter T. After the process of transcription, you have mRNA. Now, mRNA, like all RNA, is single-stranded. So you can see there that it's not double, it's only single. And there are no T's, there are U's. And then what's going to happen is this mRNA is going to go out ultimately to the ribosome. And in the process known as translation, you're going to bring these things here, which are called amino acids. They're going to be brought to the ribosome and start to build this thing called the polypeptide chain, which is ultimately going to become a protein, hence protein synthesis. Now, that's all great, but sometimes there's mistakes. And what will happen is radiation, let's say X-rays. That's why the person always goes in the other room when they do your teeth, or if you've ever hurt yourself. Our friend the sun can cause UV damage, could cause skin cancer. And if you happen to live near, once again, a nuclear power plant or something like that, gamma rays are also very dangerous. A random mistake, there could just be a mistake in the DNA, happens. Or you could have inherited it from your parents. Things like Tay-Sachs, things like sickle cell anemia, things like that you got from your parents. Okay, so let's talk about this. There always has to be an original DNA somewhere. So your original DNA, in this case, is TACGGG, you get that. This is known as the template strand. Now, the template strand is what is going to make your mRNA, which is eventually going to make your protein. So this arrow, once again, represents transcription, and you will have to do this, so definitely know what's going on, hopefully. Now, for every T, there's going to be an A. For every A, there's going to be a U, and for every C, there's going to be a G. So far, that's pretty easy, and I'm pretty sure you can all do that. So let's continue. There's going to be 3 C's, and you know that because there was 3 G's. a U, a G, and a G. Once again, no T's. U, U, U. C, C, G, and U, A, A. So all I did was I took the complementary base and I made a strand of mRNA. Now I'm going to use this thing over here, which is known as the universal genetic code. Now what we learned is every 3-pack of letters on the RNA, the mRNA, is known as a codon. Now each codon is going to equal 1 amino acid. Now you're not going to need to know the names of the amino acids, but let's say, for example, AUG. We go and find it on the chart, and it's right over here, AUG. And the amino acid is MET, or methionine. Once again, you do not need to know that. Now we go on the chart, and we find 3 C's. And 3 C's are going to be right there. It's going to be pro. And we're going to go find a U and 2 G's. And a U and 2 G's is going to be over here. That's going to be TRP. 3 U's in a row is going to be up here. Phenylalanine, PHE. CCG, once again, CCG is going to be over here. It's also proline. I want you to see something there as well, is that there are many different combinations of codons that could make the same amino acid, so that's very important. And also, or finally, UAA is right here. It's in red. That's a stop codon. So what you have just created is a polypeptide chain that has 5 amino acids long. 5 amino acids. This is a polypeptide chain. It is not a protein yet because it did not fold, but it will eventually become one. Okay, fine. If all is good and all is right in the world, your original DNA, no mistakes, everything's great. But what happens if there is a mistake? Well, let's take a look at our first mutation. Now, I kind of told you what it was. I kind of gave it away a little bit. But this is known as a base substitution. So all that means is one of those letters is going to be wrong. Now, if one of those letters is wrong, I may or may not have a problem. So what I like to do, I kind of gave this away, so we don't have to go too crazy here. But you notice the mistake is right there. So we know this is AUG, CCA this time, UGG, UUU, CCG, and then UAA. So this is still a MET, nothing changed there. CCA, all right, so now I got to change here. And there's my mistake. Now I don't know what's going to happen. Let's look. CCA is going to go get a proline. All right, well, let's see. Well, what was it? Well, it was, oh, look at that. It was a proline. See that? So, if it was a proline, did anything change? It did not. So UGG, once again, let's just go look these up. UGG is going to be TRP. UUU is PHE. CCG is pro. And then this is a stop codon. So what I just made, I have a mutation. Now this is called a base substitution because I only changed one. And it's known as, it's known as a silent mutation. Or a neutral. Silent and neutral are the same as far as you're concerned. And what happened was the change did not cause any problems. Therefore, we would say that after this mutation, the mRNA, the protein, whatever, was unaffected and it will be absolutely functional. Not one single thing changed even though we had a problem. Let's see mutation number 2. All right, so I'm looking. Again, I'm giving it away. I'm giving you a hint. I'm telling you it's a base substitution, so we're only looking for one mistake. So let's see. right there. There's my mistake right there. So I know that this is AUG now for the third time. I know that this is going to be CCC. And I know that this is going to be UGG. Now this is going to be, oops, this is going to be UUA. UUA. This is going to be CCG, and this is going to be UAA. Well, let's see what happens. We know that this is a MET. Nothing changed there. 3 C's in a row is going to be, where are my 3 C's? Proline. Okay, nothing changed there. UGG. And that was TRP. Nothing changed there. All right, so here's my change. UUA is now going to get the amino acid leucine, or LEU. Uh-oh, well, we got a problem, because if we finish this up and we go back to our original, I'm supposed to have a proline in that spot. Well, guess what? I don't have a proline in that spot. Oh, I'm sorry, wrong spot. I'm supposed to have a phenylalanine in that spot. I apologize. I'm supposed to have a PHE there. But I don't have a PHE there. I now have a LEU there. Uh-oh, that's a problem. I changed one base only, that's it. But in this case, I call it what's known as a missense substitution, because now I did change my amino acid sequence. So I will absolutely have an affected protein. Now here's what's weird. It may possibly still function. Possibly, possibly not. It may be altered, but is it possible it may still function? The answer is yes. Again, I'm not going to ask you that question. I'm just going to ask you if it's going to be affected or not. Okay? And our last one is, again, a base substitution. I'm not trying to trick you here. So let's see what we got. A, U. Oh, I guess I got to find it first, right? So check, check. Oh, here's my mistake right here. The mistake's right there. So GGG is going to be CCC. And here I'm going to have UGA. Now I already know what that is going to be a stop codon, so I don't have to worry about it anymore because it's completely done. So this is going to be MET. This one's going to be pro. This is going to be stop. Well, this is a big time problem. So it was only a base substitution. I simply changed only one base. But in this case, I got a major problem. This is called a nonsense substitution, because what I did was I did cause a change in the amino acid sequence. It is way too short now because I put a stop codon in the wrong spot. Bad, bad, bad. So when I look at my list, it will absolutely be affected. And in this case, it will be non-functional because it's way too short. And if it's that small, that means I lost a lot of amino acids, and that means that protein is not going to fold correctly. So those are our base substitutions. We can either have a neutral, we can have a missense, or we can have a nonsense. So that's that. Now, the next two are pretty annoying. I'm not going to lie to you. And they're very tricky. So this is going to be known as a frame shift. Now, frame shifts are tricky because you're either putting in an amino acid, you're putting in a base or you're taking out a base. Now, you don't look and you're like, how do I know? So what I always do is I compare, okay? Those two are the same. I like that. These two are the same. I like that. These two are the same. I like that. These are the same. I like that. But now I got a problem. Now, normally I would say, oh, there's just a substitution here. Normally that's what I would say. But you always have to look down the line there. And if you see that they're all messed up after that one switch, that means you know you have a frame shift. So let's see what our frame shift is. And in this case, it appears I put in an A. And you can see that that A was added right there because I look for a pattern. GGCAT. GGCAT. You see how I screwed everything up there? So in it went. And that's how I know that I just did an insertion. Let's find out how bad it screwed us up. This is still AUG, nothing changed there. This is still CCC, nothing changed there. This is still UGG, nothing changed there. This is going to be UUU, nothing changed there. But let's see what happens here. This is now going to be UCC, and this is going to be GUA. So let's see what we got. That's still met from the chart. CCC is still proline from the chart. UGG is still trip from the chart. UUU is still phenylalanine from the chart. But now we got a problem because UCC is going to be SER. Whoops, there's supposed to be a proline there, but there's not. And the next one's supposed to be a stop codon, but I got GUA, which is a vowel. Well, I got a problem here because if you notice, there's no stop codon here. And if there's no stop, I got a mucho big problem. So let's see. This frame shift is called an insertion. And I know that because I showed you where I added that A. And now, there's our A. Once again, we added. What happened? Well, everything shifted. And because everything shifted, now my protein is too long. Because I do not have a stop codon. My one little teeny weeny mistake really screwed everything up. So therefore, my protein is absolutely affected, way too long, totally non-functional. And the last one is also going to be a frame shift, but this is going to be a deletion. So let's look. TAC, good. 3Gs, good. ACC, good. Okay, here's my problem. So again, I would say, this is simply a base substitution, easy breezy. But then you got to look down. Every single letter is messed up after that. So therefore, I know something happened. And let's see. In this case, I actually lost an A. So because I lost an A, everybody shifted over. So let's see what happens. This is still AUG. Nothing changes there. Met. This is CCC. Nothing changes there. Still pro like it's been the last 10 times we did it. This is going to be UGG. And that's going to be trip. Once again, nothing changed there. Now we got UUC. So we go to our chart, and UUC is going to be phenylalanine. Okay, and that's fine. That's what it was. Now we got CGU, and then CGU is going to be ARG. Now we got a problem. Well, there's only 2 there, so now I got a real problem. Everything's all messed up. So because I ran out of bases, I ran out of amino acids, everything's screwed up. So once again, this is called a frame shift mutation, where in this case, I had a deletion, and you saw that I lost the letter A. What happened? Once again, this time, everybody shifted to the left this time. Now, we're too short. Wrong order, too short, definitely affected, definitely non-functional. So that is a little review on the basics of protein synthesis and mutations. So you'll have some work on that for due tomorrow. And actually, it might not be due tomorrow. It might be due in a couple of days. But we're all set. So good luck.